Hello everyone, my name is Sophie and today I'm joined here with Neil. Neil is going to be explaining to us AI validation today.
Thanks, Sophie. Well, first of all, I suppose I should confess that about 10, 15 years ago, when we first started going down this machine learning, artificial intelligence type of route, I was one of the skeptics who said we're never going to be able to validate that. So today I'm just going to eat my words. Powered by AI with the intelligence of the cloud. These sort of terms, and what they really mean is we're throwing in something which has a degree of machine learning in it, possibly from another application. So we may be including text recognition or voice recognition. We might be including predictive text, and these are usually from other apps that are already on your laptop, phone, iPad, whatever. Maybe they also include your GPS data, your location. Maybe that links to your weather. Maybe we even start bringing in your exercise data from one of your wellness or health and fitness apps. And this is all providing more data that can add some degree of additional clinical functionality. So this may become data. We might use this clinical data. We might process it somehow in the cloud. We might apply some sort of algorithm to give us some sort of measure, maybe just a traffic light scale, how fit we thought you were coming from this data, whether you lived in the town or the country. That could be important for, say, asthma or COPD. We may even do some form of database type computation on the web, adding and subtracting various bits of data, but not really doing anything that you wouldn't be used to giving your doctor, perhaps as a patient diary, just because it's using data off your phone, off your laptop. Maybe it's a little bit more accurate. And this leads us on to the idea of, well, we've got something to compare it with. We can do a benefit risk assessment, and we can determine based on that what level of validation is appropriate. And if this is coming in from a well-established app, if we're bringing in a bit of voice recognition from Siri or Alexa or Google, then maybe this is very well established. It gives a real significant benefit to the interoperability with the patient, but it actually involves very little risk. So the amount of validation we have to do is fairly small. You can quickly spot if it's wrong. Then we start moving into things that are based on data. And nearly everything we do where we're talking about artificial intelligence, we're talking about having a big data set on which to train that level of artificial intelligence. So if we're looking at machine learning, the first one we want to look at is the fixed machine learning, where you have a defined training data set. Maybe there's already existing clinical data on a large population of patients who had a who had a diagnosis of early onset dementia, and were recruited into a clinical trial to watch how this progressed over a period of time. And from these patients, we may be able to gain a lot of information by looking at the clinical data, looking at the lines or curves of best fit, and looking maybe through a least squared methods, but things that are just really school or early stage university statistical models, and saying you know, if you're like the people in our clinical trial and everything suggests you are like the people in our clinical trial, this is how the disease is likely to progress. So we build this up on a set of training data, and then we apply it to a larger set of validation data. And what we mean by validation data is usually a trial, different people, a different location, with perhaps slightly different prognosis even. Do we get, does it hold? Does it give us substantially the results we're expecting? If we look at our predictions after 3 years and where the cohort in this clinical trial were after 3 years, do they match? Have we got a useful diagnostic tool that's telling us how quickly this degree of dementia may progress if we do nothing? And then what we can do is to say, well, we're treating that as validated, and we release the product. And this is a lot of the early products that went on the market in the mid-2010s. We're starting to see they've been trained on a set of data, they've been validated on another set of data, but this is now fixed for the life of the product, and the product goes on the market, and we're simply checking with surveillance data as it moves through its product life cycle that the algorithm is still working. But to all intents and purposes, the coefficients, the variables, the algorithm all remain fixed until such point as we can say, now we know how we should refine the algorithm for a Mark II version of the product. Now, Sophie, just before I go on to the next slide, I should say, in the previous slide, I was using the size of the box to indicate the amount of clinical data that we have. But in the next slide, what I'm doing is using the size of the box to indicate the accuracy of the AI algorithm, or the accuracy we predict it's going to have. So we're going to start off with a fairly big box, and as we refine the AI algorithm, it slips down a little bit. Let's have a look at the slides and see how it works out. FDA have come up with a split now to what they term a more adaptive process, where they say, well, you know, there may be a degree of localization that goes on or could go on with these machines. If you were to put one machine and use it for early stage screening, and another machine and use that for people who already had a first diagnosis from early onset dementia, what might this look like? And it might look something like this. So in the bottom box, people exactly like the ones we had for our training and validation data. Unsurprisingly, we're starting to get the same results. In fact, we can actually say a very tighter set of results because we've now got more data points. However, if we were to look in the screening example, where you're screening an entire population earlier, we might find a very different set of results. And as we progress further in this, the differences may become more marked. So we've now got a type of data that may be sensitive to the patient population. Maybe if we have these two machines, we're now splitting into two products, one intended to be used in a screening scenario, one intended to be used in a diagnosis confirmation scenario. And those two will work best with slightly different algorithms. And now FDA says maybe what we can come up with is a predetermined change control plan, which may talk about how this algorithm may adapt and may be able to be adapted to a different environment of use, something different from our original clinical data, something that matches our new surveillance data. And this predetermined change control plan will actually hold for a significant part of the life cycle of the product, but may not be for all of the life cycle of the product, and maybe we have to update it certain places where we have a new predetermined change control plan for the next 3 years, which might be radically different to the past 3 years. As we build up the data, there should be an expectation that we become more accurate in the different clinical settings, in the different clinical use cases of this machine, and perhaps the number of variants, the number of applications, the way we use this product may change, but the core product stays the same. We also need to be very aware that we have to map out an end-of-life process, and we have to make suitable arrangements for this to be implemented. Even if the company was to fail, even if all the original development team were to leave the company, somehow we have to know that this is still being monitored, that the surveillance data is still being recorded, and that we know if there may be vigilance, there may be needs to report if we exceed that predetermined change control plan limits of what we're allowed to do. And now we're getting truly into what I think of as artificial intelligence, where we've got neural networks, where we're dealing with multiple algorithms, multiple coefficients, multiple variables. We're getting them all to interact together. So what we're trying to get into here is we're having a network that we've created that truly mimics the neural network in the brain.
Mm-hmm.
As Primo Levi described it, it's this labyrinthine tangle of yeses or nos that comes up with decisions, and somewhere has within it encoded our moral compass of how we should behave in any given situations. It also has that ability human beings have to make a catastrophic switch. Something's okay, now it offends my moral compass, now it isn't. And then we can make this switch. These are areas that we're still very much struggling with, and they're areas that we're trying to refine on the cutting edge of AI in areas like self-driving cars. Now, we haven't got any way of validating in these areas yet, because we don't really know what a moral compass for every situation is going to be. That's not something it's easy to write down as an algorithm which we can verify, which we can validate. The best we can do with things like self-driving cars is to have limited experiments in areas like California or Milton Keynes in the UK and see how they go, and at least make the assumption they're not going to be any worse than a human driver. That clearly isn't going to be good enough for AI in medical devices, and we're going to need to have a much better idea of how to validate the behaviour of neural networks. We're not there yet.
Thank you so much, Neil, for all your explanations today on validation. We'll be here same time next week.
See you there. Bye.